So, I'm going to be kind of honest. It was a little mean to put me first. See, I'm from sunny San Francisco, California, which looks a little like this right now because out on the West Coast, it's currently 6 in the morning. And I am not a morning person. As a matter of fact, all of my clocks look a little something like this. I didn't even know there was a 6 in the morning. And I'm telling you this to give you fair warning up front. I get a little sarcastic when I'm tired. And so while many of you probably think you know what I'm going to talk about today, I think you might actually be a little surprised. My first thought was, well, this is a conference. I could introduce a new product, right? Conferences are great places to do exactly that. But this isn't really that kind of conference. This is the Clojure Conj. And the Conj is about sort of deep technical knowledge, right? This is about us talking about the things we use to do work. And that is a very serious thing. And so my thought was, if we're going to be serious, let's start with little color-changing men. This past weekend, my girlfriend, my co-founder, and I set out to save the universe, if you will, by building a game in a 48-hour coding competition. And what we came up with was called Chroma Shift. And it looked a little something like this. Sorry, it's a little hard to see, but you're this little tiny guy who changes color. And when you change color, you turn things in the world on and off. And so what's kind of neat about this game is that it's actually a multiplayer game where you're both racing to some goal. And as you change colors, you actually affect the other player's world. Now, I mentioned this was for a coding competition, and that competition is called the Node Knockout. And the rules in the Node Knockout are relatively simple. You have 48 hours. All digital assets have to be created in that 48 hours. All the art, if you have sound, all the music, all of that stuff must be created in that 48 hours. Past that, you basically have free reign. You can build anything you want, so long as it's built on top of this newfangled JavaScript platform everyone's talking about called Node.js. And so we entered this JavaScript competition. But there's nothing in the rules that said you have to actually write it in JavaScript, just that it needs to run in JavaScript. And so we decided to cheat a little bit, and we used ClojureScript to do all of this. And you may have heard the adage before, bringing a knife to a gunfight. Well, we decided to bring something with a little bit more kick to it. For those of you who don't know, ClojureScript is a version of Clojure that compiles down to JavaScript. And so what that means is we bring the wonders of macros and persistent data structures and sane semantics to the otherwise scary and unpredictable place that is JavaScript. And so we built a game with ClojureScript. Now, how many people here, show of hands, have actually built a game before? Something more than Pong, because that can be done in 100 lines. There went, a lot of hands just went down. For those of you who haven't before, I highly recommend you build a game. It turns out that building games requires a very different way of thinking about software. And it sort of stretches your mind a little bit. On top of that, it actually serves as a fantastic way to sort of test the edges of performance of a language and a platform, right? Because games have to be fast. And when I say fast, I mean really, really fast. As a matter of fact, all of your logic, all of your physics, all of your rendering has to get done in less than 16 milliseconds in order for you to maintain 60 frames per second. That is not a lot of time. As a matter of fact, if you try to iterate over about, I think, 1,000 to 10,000 items in a seek, you'll hit this by default. So here we are. We have this ClojureScript, or we have this competition. We want to build a game in ClojureScript. And so the question comes down to, how do you build a game that feels Clojure-y, right? You don't want to write something that looks just like JavaScript. You want something that feels Clojure-y that is still blazingly fast. There are a few different schools of thought when it comes to game design. Sort of the traditional one is that you have these really deep object hierarchies, right? Because games were traditionally built in C++, and so OOP is the way of the land. But it turns out those get really hairy, and they're scary things in the long run, because you want to make some new sort of enemy class, and you have n different base classes for your enemy, and it turns out you end up overriding everything all the time, and it just ends up being a mess really, really fast. It's also not a very Clojure-y way to build something. But there is another way of going about building a game engine that I do think fits Clojure really, really well. And that is called a component entity system engine. I think the easiest way, instead of trying to give you a high-level overview of what this is actually the easiest way to understand it is to go through each thing individually. And interestingly enough, we're going to start in the middle, because it's by far the simplest. Entities are just IDs, right? So everything in the game gets some ID, literally a number, an integer, right? Instead of having sort of these monolithic game objects that you think about, like let's say you wanted to represent a player, and you think about all the things that go into a player. Well, you would have X position, Y position, the angle of rotation, his health, his walk speed, and other different attributes that you would have to represent. You end up with these giant objects. The notion here is that instead, the only thing you pass around is this ID. And what you want to do is decompose all of that state into little tiny reusable pieces. Sounds very Clojure-y, right? Those little tiny reusable pieces of state are called components. And what's nice about this is that the strategy here is that they can be reused. And so they need to be single-purposed, little tiny bits of state. An example of this would be position. And so here's a little code from the game, right? We want to create a component for position. It's going to have an x coordinate, a y coordinate, and a is an angle of rotation. Wasn't really important for our game, but useful nonetheless. And so we have this little tiny bit of state representing position, and we would have little tiny bits of state representing all the other different things we want in the game, walking and jumping and all these abilities that you might have as a player. By sort of decomposing this monolithic object, it makes it really, really easy for us to create new things. So let's say, for example, in our game we wanted two bad guys. One that was really, really fast and walked around, and another one that was slow but jumped every 3 seconds. Well, if you were doing some crazy object-oriented thing, you would probably have to, extract some base class that represents the basic methods that this guy would have, and then override some of them so that he jumps. But in a component entity system, since components, when you think about it, an entire entity is nothing more than a group of these components, all you would have to do is something like this. Right? So if we wanted a fast guy, we would give him some set of components. In this case, he has a position, and he has this walker component that gives us speed, right? And 20 units is apparently really fast. And then you have a jump guy who has similar components, but done slightly differently. He has a position, he's a walker, and he is a jumper, and he'll jump every 3 seconds. That's all there is to creating something new, right? This ability to compose these together very cleanly. Well, underlying this system is nothing more, when you think about it, is nothing more than some basic data structure that allows you to map entity IDs to these groups of components. Right? That's all you really need to keep track of all of this stuff. And that's very, very easy to represent inside of Clojure. All you need to do is have a map from entity ID to a vector or a map of these different little component maps, if you will. So this gives us all the data we need for our game, but we haven't actually talked about how the game does anything, right? This is just sort of what the game is. To do that, we need our last piece, and that is the system. It is the logic. Now, unlike in an object-oriented system where every single class would be responsible for, handling its tick events, right? Because in a game loop, you're constantly looping over every single thing in the game. What we want here is nice little bite-sized functions that work over those components, right? Those components are kind of like tags for us. They let us know what entities inside of the game need to react to different things. And so I think the best way to look at a system is to just be very practical and look at a real system. So we need a component here, and a game isn't very fun if you don't actually render something to the screen, and so our component is renderable. And as you can see, all it does is it takes a function that you would use to render. And so what our system needs to do is it needs to go and look at all of the entities that are renderable, go through each one of them, get the renderable component from it, and call that function, right? Sounds really straightforward, sounds like a simple function, and it is. This is what it would look like. You have some renderer, which is just a regular old Clojure function, and you do seek over the renderables so that you have each entity that's renderable. As just takes an entity and turns it into the component that is represented by that type, in this case, renderable, and you would call that function with the entity itself. So there you have it. That's all it would take to make something renderable. So let's say you add some new thing to the game and you want it to be visible on screen. All you'd have to do is add this component, right? If you add 20 different things to the game and you only want half of them to be renderable, you just don't give them the component. That's all there is to it. There's no overriding. There's no sort of crazy class nonsense going on there. And then inside of the game, or rather inside of the game loop, what you end up doing is you just call this renderer function every single frame, right? And this all E function is just saying, give me all entities that are renderable. That's all it takes to make a renderable system. So that's great. We now have a way of sort of organizing our thoughts in our code into something that feels Clojure-y, right? We have this component entity system engine. Hopefully it's kind of started to set in a little bit why this might be a good idea for Clojure. I can't remember exactly who said this. I'm pretty sure it was at the last conj, but this is about turning the entire game into data, right? This is dataing all the things. And when you think about it, that's a great place for Clojure to be. All we have is some giant data structure that represents the entire game at runtime. And then we have these nice little bite-sized functions that work over that structure. Data, functions. This is the bread and butter of Clojure, right? And what we get as a result of this, kind of like I was saying, is that we get composition in really, really neat and interesting ways. It's trivial for us to change the game even at runtime. And so here's a little excerpt, I guess, of the code from the game itself, which is on my GitHub if you want to go look at it. From an actual level inside of the game, right? So we had some background here. It's renderable. It's on the backing layer because there's the visual layer system, so you don't cover the player up when you're rendering things. There's a camera, which isn't something that gets rendered inside of the game, but you want it to have a position, right? Because you want it to follow the player around the game world. And then you have the player itself, which again, instead of some monolithic object in and of itself, is a bunch of these components all strung together. Things like, yes, he's renderable, but he responds to keyboard input. He has a color. He's animated and standing right by default, and so on and so forth. Now, I mentioned composition here. This is a multiplayer game, and what's really neat about how that played out for us is that in order to implement the other guy, all we had to do was take this this set of things and remove some of them, right? Because fundamentally, that other player needs to respond to the world much the same way that the normal player does. But he's not going to respond to keyboard input, and he might have a couple of other things involved in there. He might respond to syncing, right, over the network. And so supporting multiplayer was relatively trivial in that regard. So great. Component entity system engine. So this is the way we're going to build the game in ClojureScript, or this is the way we built our game in ClojureScript. But there's another aspect to this as well. And that is, remember, it doesn't just need to be Clojure, it also needs to be really fast. And when it comes to Clojure or ClojureScript in our case, there are a few problems with this approach that make this kind of difficult. The first is that components change a lot. Every single frame you're going to be, changing state inside of the game, right? You're going to be getting new positions. You might have new velocity vectors and so on and so forth. Because there are so many little components, you're recreating these all the time. And the second thing is that you need to iterate over these entities, because of the way we've sort of decoupled it, hundreds of times in a single frame, right? And like I said, you need to do all of this in 16 milliseconds. And the problem you run into with ClojureScript specifically is seeks can't go that fast. There's just too much overhead with calling first and all of the functions that go involved with that. You can't iterate over them that quickly. And the second thing is persistent collections are not necessarily too slow to write to, although they are sort of on the edge here for this. But more importantly, they're a GC nightmare in this case, because you're creating thousands of objects every 16 milliseconds. It doesn't take very long for the JavaScript garbage collector to freak out, go through some GC pause, and you've basically ruined your game. Fortunately for us, being on top of ClojureScript, this isn't that big of a deal because we have access to all of JavaScript. And JavaScript arrays and JavaScript objects are pretty darn fast. They are really, really fast, actually. More than fast enough for us to hit our 16 milliseconds. But ClojureScript is Clojure, right? It's built on top of the abstractions we have come to know and love inside of Clojure. And so it's not really designed to work over JavaScript arrays and objects. If you start writing this code, it ends up looking pretty nasty. It doesn't look like Clojure anymore. But it is Clojure. And so we have the benefit of macros. They can come to our rescue here and make this code look exactly like Clojure, even though we are working with these arrays and objects. And so sort of to give you an example of this, I'll show you an example, a real system from the game itself using this, right? So when you change color, we need to turn all of the similarly colored things on or off, right? So there's this flip active system. And it takes color and sort of whether or not it's active. And then what it does is it goes through this DOFS macro is for do fast, right? It's just do seek over arrays. Nothing fancy here at all. There's a let see macro. Since you're constantly pulling components out of these entities, right? I wrote this little macro that just makes that really clean for you instead of constantly writing let, some entity as blah over and over again. And then we have exclamation point and question mark. Those are just simple aliases for a set and a get, array set and array get, since JavaScript objects are weird. That's all it takes. And this still looks like Clojure, right? This looks like code you would have written. It looks like the example I gave before, more or less. So that's awesome. Using JavaScript arrays, using JavaScript objects with this component entity system, we've got a game that is not only fast, but is built on the founding principles of data and composition. That's exactly where we want to be. Now, the entire code base for this in that 48 hours ended up being about 2,300 lines, which for ClojureScript is a lot. But I should say that easily 500 to 1,000 of those lines are just the definitions of the game or sort of the game levels themselves, right? And so when you start thinking about that and you separate out some of the physics stuff that you wouldn't ever rewrite, you're probably talking about having written this entire multiplayer game for the Node knockout in about 700 lines of code. I'd call that pretty good. That being said, it wasn't all fun and games while we were doing it. We definitely ran into some things. And even though I've worked with ClojureScript a lot, I still don't know what to do with this. Right? You get these crazy error messages that make literally no sense whatsoever, that are almost impossible to figure out because for whatever reason, sometimes the Clojure compiler, not the Clojure, the Google Clojure compiler, will take all of your lines of code and put it onto one line for a while, or take 10 lines of code and put it onto a single line. And so you'll have 20 dot calls in that single line. You have no idea which one of them is not available to you at that point in time, and it doesn't give you any help for trying to figure it out. That being said, it obviously wasn't that much of a hindrance. We were, after all, able to build a game in 48 hours. And so that speaks really well to not only the ability for ClojureScript to be performant, but also for it to work well in sort of a pressure situation that not many people have worked with before. So I've been telling you about this game, and many of you may be wondering, well, what in the world is he doing up on stage talking about a game and not light table? We built the game with light table, and we learned a lot doing that. We found out some of the brokennesses and some of the things we need to fix in order for this to work a little bit better. But that's not really what ties this together. I have a confession to make. And that is that I haven't really been doing much Clojure lately. I've kind of taken to another language. And actually, to make Kevin Lina proud, I'll show you a graph. As you can see, I'm basically doing almost no Clojure now. It might come as a shock to you that I'm instead doing ClojureScript. But what's interesting is I'm doing all ClojureScript, basically. And that means for Lighttable, too. The latest release of Lighttable is entirely built with ClojureScript. The only bits of Clojure that exist are in the lining and plugin that you use to connect to projects. That's it. And the way we managed to do this is by using a really neat project that embeds Node.js into Chromium directly. And this project is called Node WebKit. It's really cool. It's written by these guys out of the Intel Open Source Center. It's really young. It's still got a lot to work on, and obviously we had some issues with it when we released with Linux and so on and so forth. But it's a very good way of sort of essentially giving yourself a platform to build ClojureScript client apps on top of. And so here I am doing tons and tons of ClojureScript, very little Clojure. But this isn't the only thing that links the game to Lighttable itself. It's not just that we built the game in Lighttable. It's not just that it's all ClojureScript now. It turns out that this sort of component entity system thing is a pretty good idea, not just for games. This actually served as the inspiration for how all of Lighttable is now built. But Lighttable isn't a game, and so there isn't a loop, right? There are events. It's just like you would expect any client application to be. It's an evented sort of system. And so while this component engine works really well for games, it needs to take a slightly different form when you start working in a world without that loop. And the way this sort of got implemented inside of Lighttable is fairly simple. It is a behavior object system, as I'm calling it. And again, we'll just kind of go through these and get a sense for what that might mean. An object is sort of the first bit here. And unlike in a game where you're going to have lots of these composable bits of state, objects inside of Lighttable aren't really going to be very composable in the state sense, right? Not every object has position and so on and so forth. That doesn't really make sense. Instead, state is just a map, right? It's just a map with things like, you could imagine the map for an editor, for instance, might be the path to the file it represents, if it is a file. Sort of what language what language mode it's in, and so on and so forth. Now, everything inside of Lighttable is an object. Everything, from the background to the it's kind of hard to see, unfortunately. From the background to the tabs to the editors to the results windows, the command bar, everything is an object. What's interesting about that means you can easily add and remove the entirety of Lighttable if you wanted to, fairly trivially. And sort of the way this plays itself out in code, remember these are just little maps of state, more or less, but there's some special things we need to do. So there's this function that you use to write them. And so this is what an actual object inside of Lighttable looks like. So this object is the console. That's the little thing that prints out all your results for you. And it just has some metadata on top of it. So this triggers thing is just saying there are going to be events that can be called on this thing. In this case, there aren't any, but if there were, you would want to document them here just so you have a good sense for yourself. There's this set of behaviors, and remember, these are just maps. These are just state, and so behaviors are what are going to give it some life. We'll talk about that in just a second. And the last thing is all objects have an init function. They can choose to do nothing when they're initialized, and that's fine. But if they do something, whatever they return is tried to be considered their UI. Right? And so in this case, with our console, we just return the console UI. So we have these objects, these maps, and these get put into a nice big data structure for us. But we also need a way for these objects to do something. And that's where behaviors come in. And a good way to think about behaviors is just sort of named event handlers. They're kind of a way of composing reactions to things. And so I think the easiest way to understand that is just to look at one, and it looks pretty much like what you would expect. You have some behavior, and give it some name. So when you click something, we're going to remove it. So we call it onClickRemove. And remember I said triggers are the sort of events that get raised on an object. And so the trigger in this case that we're concerned with is click, right? So when we click on something, or rather when the object raises click, or click is raised on the object, we will have the following reaction. And that reaction is to call this rem exclamation point function. So this is, again, just like that component system, this is about turning everything into data, even when something happens or whether something happens as an event, right? I mean, if you think about how events would get built, or how event systems work sort of traditionally, you give something an object. You say, okay, add this event handler to this list, this nameless list of event handlers, and you're kind of lost at that point. If you wanted to introspect that object and see, oh, what things are going to happen when I click on it, you can't really, right? You could get a list that says, oh, there are 3 functions that are going to get called, but that's it. Whereas in this case, we've dataed it, right? We can know exactly what is going to get called when something happens. And so here's how this plays out in a real object. So this is the notifier object, the little thing that shows up in the bottom right-hand side of Lighttable when there's a new version or when you're connecting or whatever the case may be. And so we've documented a set of triggers for it, right? So the things that might get called on this object are notifo.click, notification.click, and notification.timeout. So if you click on one, we want to know about it, and if it times out, we want to know about it. And then we have these behaviors that we're saying it has. Well, when we create this object, go ahead and add the behavior remove on timeout, and that's going to listen for that notification.timeout trigger, right? And it's going to have remove on click. Now let's say, for instance, you didn't like this behavior whatsoever. You wanted to change the way notifications worked inside of Lighttable. All it would take is removing those behaviors. That's it. You'd remove them, add new ones. Hell, you don't have to add anything, right? If you don't like that they time out, just remove that behavior or add some new one that gives it a totally different way of working. We have composition here again. This is about being able to compose these events in sort of unique and interesting ways, and it can happen at runtime, which is really, really powerful. And so an example of this sort of being able to compose these behaviors together is, let's say we wanted to make every single editor inside of Lighttable an instant evaluation environment. Basically, you want to make every single editor an insta-REPL. All it would take is adding these 3 behaviors to it. So sonar result is the thing that does the magical figure out what the values are and put them in their place. Every time it changes, every time the editor changes, you want to eval. That's pretty straightforward. And you want to be able to toggle the live eval on and off. Those 3 things are enough to essentially give every single editor inside of Lighttable the ability to be an insta-REPL. And so what we have is just one big data structure. All of Lighttable is in this single map that represents every single object. And what we get as a result of this is we get introspection for free. This is a little tool that I have built where I can click on any object inside of Lighttable and then see everything I know about it, right? I can see all of the behaviors it has. In this case, it's an editor, and so I can see things like, well, it has no wrap on. It's going to be destroyed when it gets closed. It's trying to track whether or not it's active. It has the ability to save because it's file-oriented. You can eval. It's going to save when it gets evaled, and so on and so forth. If I wanted to change this, I don't even have to go to the code. I could click on one of these, hit an X button, or hit some button that removes that behavior, and then go look at a list of all the behaviors that I have available to me and add it. There you go. Now I've changed the functionality of this editor entirely. And so this is the system that underlies Lighttable. It is the behavior object system. And like I said, it draws a lot of inspiration from that component way of building games. We get runtime modifiability and infinite customization, 2 things that are really, really hard to get, right? But fortunately, games have sort of solved this problem for us already. And so that's how Lighttable works. Now, I always like to leave a fair amount of time for questions, but I have one more thing that I want to talk, and since we started early, I should have quite a bit of time for questions. But I want to sort of end on one more thing, And that is, since I'm doing a lot of ClojureScript, and I'm fairly certain that Lighttable is probably the biggest ClojureScript application out there, I wanted to sort of end on my 5 wishes for the project itself. My 5 wishes for ClojureScript sort of span a bunch of different things. The first one is that we need better error messages. And I know why we don't have them. It's because this is a really, really hard problem to solve, given the way it works. But we have to fix them if we expect more people to be able to do this. I literally spend hundreds of hours doing ClojureScript, and I still get tripped up on errors, right? If that's happening to me, if you're new to it, that's going to make things kind of difficult. Now, that being said, for the most part, you only run into this every once in a while. But when you do run into it, it's very hard to get around. And so this is something I think we really have to sort of focus on. The second one is that I would really, really like to see the compiler working on Node.js. Now, I'm not talking about eval here or any of that stuff, just the compiler. I want to be able to take ClojureScript code and turn it into JavaScript without ever being able to spin up the JVM. And interestingly enough, when I talk to people about ClojureScript, one of the biggest complaints I hear, for whatever reason, is that they don't want to take that Java requirement. They just won't do it, right? I write in JavaScript. Why in the world am I spinning up the JVM to do that? It's by far the biggest criticism I hear. But on top of that, in terms of Lighttable, it would be amazing to be able to modify Lighttable itself without ever spinning up the JVM, right? I would love not to have that dependency, and that would make a big difference. I don't even think this is actually that bad. We'd have to come up with some interesting things to do with the Google Clojure compiler, but I think even there's some clever things we can do. The third thing is, I would really like to see the ClojureScript analyzer being able to work over Clojure. It may not have the same level of information that the Clojure analyzer has, but the ClojureScript analyzer has a far better interface as it exists now. And there's only superficial things keeping this from really happening. I don't think there's a lot of work here. The main one is that the namespaces have some different things inside of them, right? So like the ClojureScript analyzer doesn't know about importing Java things, and the Clojure analyzer doesn't know about requiring macros. And so there's a little bit of magic we would have to do there. But this would mean that our tools could sort of rely on a single source of analysis and do really great things over top of that. And I think that would be immensely valuable. The fourth one is a bit more of a community thing, and this goes for both Clojure and ClojureScript. In just completely in general, we need screencasts. We as a community, for whatever reason, we're starting to work on the documentation. There's some great sort of efforts happening there on working on Clojure docs and so on and so forth. But we still don't actually ever show people things. We only ever tell them. And this is a big thing that when I introduce someone to Clojure, for whatever reason, I think this comes from like the way Rails became popular and so on and so forth. People go, well, where's the screencast? Like, well, we don't really have very many of those. Oh, okay, well, tell me when you get screencasts and maybe I'll look at them. So this is something that we as a community, it doesn't matter if you're building something stupid and trivial and just for fun. Like, video recording is still probably actually useful for somebody. And it's not really that hard to do. So I would really like to see us sort of build, or rather do more screencasts. And the last one falls on me a bit. And that is, we really need better tools for ClojureScript. There are still too many things you have to know, too many things for someone who's never used Clojure before to get up and running with ClojureScript, right? It's gotten tons better. Line CLJS build is awesome, and that has worked out really well. But that works really well for those of us who already have lining installed, who are already Clojure people. And so one of the things I really kind of want to work on with Lighttable itself is that we need better tools for ClojureScript and what those might look like. So those are my 5 wishes. We need better errors to help people so they're not banging their heads against the wall the whole time. Having the compiler on Node is just useful to drop that JVM dependency, which is a big blocker for a lot of people. Using the CLJS analyzer for Clojure is just goodness because we have one source of analysis, and that's very valuable. Doing more screencasts, again, that's more of a community thing, and I really, really hope you guys do it. Myself included, right? We need to start doing screencasts for Lighttable as well. And the 5th one is better tools, and again, that's kind of on me, but there's lots of interesting sort of efforts being made in this tool space for Clojure. There's a lot of work going on nREPL. Hugo's been working on like RITS, the debugger for Clojure and Emacs, so there's some good things happening here. And so since they put me first, I want to end on one last thing. And that is, I sincerely hope you realize how magical this community really is. And I'm not saying that ironically, I mean it, and genuinely mean it. Like, the things and the people you will meet, or rather the things you will hear about and the people you will meet at this conference, it's just amazing and ridiculous, some of the things that are going on in this community. Like, we're testing the waters in so many different directions, from logic programming to new tools to new databases, right? There's so much going on in this community. And I genuinely believe that we are kind of in a transitional period in our industry, that a lot of the things that we decide sort of in the next couple of years are going to make a big difference for the next decade of programming. And I truly believe that some of the people who are going to make that difference are in this room right now. And with that, I want to welcome you to the Conj 2012. Thank you. So it looks like we have about 10 minutes left. So I can take questions for about 10 minutes. Or if there are none, I will happily go sit down and go to sleep. Yeah, so the question is, for the video, if there is a video, is with the initial release of Lighttable, with that 0.1 release of Lighttable, we were trying out some interesting things with like this table mode that had this very function-oriented thing. And he was asking, with this new one, you seem to have reverted back to more of the traditional editor style with files and so on and so forth. To that, I will say it's because we wanted to release something that had a bit more polish, that worked in a more general case. But that is not to say that we aren't bringing all of that back, right? We essentially rewrote the entire thing. And one of the things we really wanted to focus on was that we need to be working in Lighttable all the time ourselves. And in order to do that really early on, we needed the simplest possible way to do that, and that was with files, right? Those tabs that are in the top of on the top of Lighttable, those can contain anything. They're not file-oriented, they're not editor-oriented, they can be anything, right? When you think about it, tabs are nothing more than a way of sort of bite-sizing a context. It's like the ability to switch between contexts relatively trivially. In Lightable's case, those contexts right now are only a file-based editor and the insta-REPL. What that ultimately intends to be is things like that, what we were calling codexes, those function-oriented sort of documents, if you will. Those are all going to come back. But one of the things we kind of learned watching people use that thing is we hadn't figured it out yet, right? We had something that worked, but it only sort of worked. We need sort of better navigation, better ways of finding those functions, and so on and so forth. And so it wasn't worth us spending all that time trying to get that into this release. We thought it would be better off, let's just release the file stuff that we have and let people use that. And that's been really beneficial to a lot of people, I think, purely because until we really figure that out, until we nail that sort of experience with the functions, it's hard to use. Other questions? Yeah. Yeah, so the question is, have I thought about how we envision extending and plugging into Lighttable? This entire object, or this behavior object system, is exactly that, right? The point is, not only, I guess one of the advantages you have of something like Emacs, right, is that you can basically turn it into anything you want. And there are two things we set out to do with Lighttable. One, connect you to your project. That's something pretty much everyone here understands. The other one is that we need an infinitely customizable interface that still does graphics, right? Like Emacs can do text, and that's wonderful and great, and Vim can do text, and that's wonderful and great. But we need to be able to, like, when we ask a question about performance, let's see a graph, right? Like, we want that ability. And so this behavior object system is a way of not only customizing the objects that are already in Lighttable, which there will be a lot of, right? There's going to be all sorts of useful, I guess, primitives, if you will. But on top of that, you have the exact same system at your disposal that all of Lighttable is built in. And I was only half joking when I said you could remove everything inside of Lighttable, right? One of the things I sort of realized is that I accidentally stumbled on a way of building a ClojureScript platform, right? You could take Lighttable, build your entire application live inside of it, right? And then just ship it as essentially a plugin that removes all the Lighttable parts, and there's your application. And I actually think that's a really strong and powerful thing to do based on how our development work with Lighttable itself has been going. And so from that standpoint, there's still a lot to figure out, like how are we going to do the packaging and of extensions and all that. But there's a lot of good sort of precedence there for what has worked and what hasn't. Right? For example, TextMate kind of screwed up in not having a central repository for these to begin with. That's something we'll not make the mistake of, right? But in terms of the actual mechanism itself, everything that we can do, you can do. Oh, I see. Okay, so he's basically saying since we're exposing the entirety of Lighttable to you, isn't that a problem for compatibility over time? My answer is yes, it would be, right? Fortunately, in general, though, the state, like when you think about state in this case, there's very little of it, for one, right? Like editors don't actually carry around that much state. Aside from obviously the text and stuff inside of them. But in terms of things outside of that, there's not that much there. And so the probability of that changing is relatively low. On top of that, all the functionality, all the scary things are still wrapped up in these behaviors you can just remove, right? So even if large things happen to Lighttable itself, there's a good chance that it actually won't be that impactful in general. And on top of that, let's say like a key changes, for example, inside of that map. In that case, you could do some shimming, if you will, and create a fairly simplistic compatibility layer that wouldn't be hard. That being said, anything that's this open is naturally going to have issues if you rely on low-level things. Like, there's nothing you can do about that. Yeah, so his question was, with the big data structure, do we try to keep it fully serializable? I've gone back and forth on that one. So I'm going to answer your last question first. Do I think it's valuable that could be serializable? My answer to that would be absolutely. I think that would be valuable. Because then what you could essentially do is package that up and ship it. Right? You could ship it to some other version of Lighttable or some other instance of Lighttable, and ta-da, you're in the exact same place you were before. I don't know that dream is certainly something I want to see happen. Whether or not the entire data structure needs to be serializable to do that, I don't think so. A view of it needs to be. You need to be able to recreate the things that, for whatever reason, can't be serialized. And it turns out that those are relatively few and straightforward, and they're things that you wouldn't want to serialize anyways in the Lighttable case so far. And so the ability to not only just like share it to someone else, but even like to sync it across multiples, like for pair programming, for example, is definitely something I want to see. And so our goal is to keep it as serializable as possible such that when we do that work, it's not that hard to do. So I talked to David Nolan, who I hope is here somewhere, a little bit about this. So his question was what does it take to make the ClojureScript compiler work inside of JavaScript, essentially? So there are a couple of different aspects to this. Just turning ClojureScript into JavaScript is relatively straightforward. The things that would need to happen there is you need macro expansion, which is something that's not written in Clojure right now. You would need a full line numbering pushback reader and that as well. I think those were the main two things that needed to happen, if I remember correctly. Someone else might know better than I do. And then there's this problem with, if you want to then subsequently get the output you would actually get if you were using the compiler, you have to run it through the Google Clojure compiler. And that requires Java right now. So I said there's probably some trickery we could do there. Well, you could easily set up, there actually already is a service where you could just send code and get the result back, right? So you could do it that way. But in your case, if you're just doing something like a REPL, right, you want to make Chimera be completely, just right, you can make, right, and I think that was actually the point of Chimera. Focus can probably talk more about it, right, was this idea that you could just like send code to it and get results back. So I don't think there's a lot of work to do there. Well, I say a lot. I don't know how much is involved in trying to do all of that. But it doesn't seem, at least on the surface level, to be too much work. All right, guys, I'm out of time. I'm more than happy. I'll be here the entire conference, so you're more than welcome to come and talk to me. Thanks, everyone.